Okay, that. So let me repeat quickly. So before the introduction of weak neutral currents, only two processes could be possible to describe the electron-positron into W plus W minus process. One was a T-channel pure charged current weak process with the exchange of a virtual neutrino, and the other was an S-channel purely electromagnetic with the exchange of a photon. Now, with only these two diagrams, the cross-section is found to diverge, so to violate unitarity. And so the problem is elegantly solved by the introduction of this third diagram with the exchange of a Z boson, which interferes negatively with the other two, okay? And in fact, now you can now compare your prediction with and without this third diagram compared with experimental data. So without the third diagram, which involves a coupling between the Z and the two Ws, the cross-section, as you can see, diverges at increasing energy. Whereas the data tell you something different, okay? The cross-section at a certain point saturates to a certain value. And in fact, this is what you obtain when you also include this diagram. So including this, then you can compare your theoretical prediction, which is the full line, with your data and define finally perfect match, okay? So there was indeed a need, okay, for neutral currents, just to solve this problem here. And the existence of this Z, W plus, W minus vertex is indeed crucial, okay, to describe the data, whereas there is no evidence at all for couplings with the Z and the photon or with the Z itself, so self-couplings. These are not observed. Now, let me tell you a few main features about the network currents, and we will, of course, go into detail today and also next week. So like the photon, the Z0 can be exchanged in T-channel, like the one you see here, processes, where essentially the identity of the interacting fermions remain unchanged. Okay, so this is, for instance, a neutrino-electron weak scattering, okay, mediated by the Z0. The neutrino remains neutrino, the electron remains an electron, and charge is conserved, of course, and is not changed. Or, like the photon, the Z can also be exchanged in S-channel, resulting in annihilation processes. For instance, E plus E minus can annihilate into, if you have enough energy in the center of mass, can annihilate into a Z0, which can further decay into a fermion-antifermion pair. Okay. And you see here some examples. So the first and the last one are depicted here in the diagrams, and then you can also have many other examples here. Few other more important properties. So the Z couples to both the left and the right fermions. And this is a big difference with respect to the charged currents. We know the charged currents, so the Ws, only couple with left-handed fermions and right-handed anti-fermions, whereas the Z couples to both left-handed and right-handed, although with different strengths. Okay, so parity, of course, is still violated also in neutral currents, but in a different way. Then the Z couples with the Ws, and this we have seen in the diagram before, okay, the one that solved the problem of the unitarity of the cross-section. And then the Z is found indeed not to couple with the photon nor with itself. Now we can compare indeed electromagnetic and neutral, weak neutral current processes. And in fact, if the energy is enough for both to be possible, then the two are interchangeable. Okay, in the sense that if you have your electromagnetic process, like the annihilation of electron-positron into some plasma minus, for instance, then you can just interchange your photon with the Z0, and you get a real process. Okay, of course, different because now it is mediated by weak interaction, but still initial states are the same, final states are the same, and the process that you get is different. Of course, the difference is in the propagator because you are propagating a different boson. So in the first case, the matrix element will be proportional to the square of the electric charge divided by Q square. This Q square dependence is, of course, the propagator of the photon. In the other diagram, of course, we don't care anymore about the electron charge, okay, because this is not anymore an electromagnetic process, but it's a weak process. So we have to include here a new coupling, the coupling of the Z0, GZ, that we will study next week. And then, of course, different from the photon, the Z is massive, actually very massive, 91 GeV. So we have to include also a mass term in the propagator. as we discussed already for the Ws. And so we can compare now the two, okay, in different energy regimes. So clearly the photon dominates at small energy. When Q is much smaller than Z, the propagator of the Z is, of course, dumped by the large mass of the Z in the denominator. Okay, so at small energy, of course, this is the dominant process, and this is highly suppressed. On the contrary, at very large energy, so when Q square is much larger than the mass of the squared mass of the Z, then it is now Q squared that becomes, it is now the mass of the Z that becomes irrelevant. The two propagator now becomes quite similar. And in fact, this is the region of the electroweak unification, where essentially electromagnetic and weak interaction unifies, as we will study next week. And so essentially the strength of these the probability of these two processes becomes essentially comparable or even equal. And then, of course, there is a region around the mass of the Z, which is around 90 GeV, where this process highly dominates, because as we will study today, we will populate a huge resonance, the resonance of the Z bond. And in that region, of course, the electromagnetic contribution is negligible. Okay, we will see this later. Now, so so the network currents were predicted in theory to solve this unitarity problem of the cross-section, but then of course they had to be discovered experimentally, otherwise it does make no sense. And the discovery of the neutral current, so not of the Z0 boson, but of the neutral currents, occurred at CERN in 1973 with the Gargamel experiment. So the Gargamel detector was a huge, heavy liquid bubble chamber, which was exposed to a beam of high energy muon neutrinos or muon antineutrinos, produced as a secondary beam at CERN. And all these, okay, so inside this vessel here, there were 18 tons of freon at high pressure, 10 to 15 atmosphere, within, as you see here, the coils, within a strong magnetic field of order of 2 Tesla. Okay, the bubble chamber, of course, allows to track, to observe the tracks of the charged particles, okay, as you know, and to photograph the tracks. And the tracks are bent due to the presence of the magnetic field, so you can also reconstruct the momentum in this way. So, what did you observe? They observed two kind of, let's say, rare and strange events, kind of events. The first one is an event like the one you see here, okay? So there is an incoming neutrino, which is our neutrino beam, which is of course invisible in the bubble chamber, does not leave any track, okay? Then at a certain point, you start to observe an electromagnetic shower. So we see the track of an electron, which radiates a Bremsstrahlung photon, which produces a pair of electron positrons, which radiate photons, blah, blah, blah. Okay, so you have an electromagnetic shower that you can see here in this photograph made inside the bubble chamber. And then, of course, the neutrino goes straight away. So this is an interaction between the incoming neutrino and one of the atomic electrons of the friend inside the bubble chamber. Okay. What you don't observe in the final state is the muon. So you don't observe the neutrino because, of course, you cannot detect the neutrino in the bubble chamber. But if a muon would have been created here, okay, so this would have been a charged current process where the muon neutrino converts into a muon, right, with the emission of a W, which can decay. But since we don't observe a muon in the final state, this cannot be a charged current process. This can only be a neutral current process, okay, like the one you see here. So it is a muon antineutrino electron scattering, which occurs through the exchange of a Z. And in the final state, we don't observe the muon, but nothing, because we don't observe the neutrino force. Okay, is that clear? And then there was also another category of results, of events, okay, with a different topology. I like the one you see here in the picture. So essentially, in this case, from your interaction of a neutrino beam with whatever it is in the freon, at the end you obtain essentially only charged hadrons, okay, tracks of charged hadrons. Of course, there are also neutral hadrons produced in between that are not observed in the bubble chamber. So how can we understand this? Again, we don't observe muons in the final state, okay? So again, our neutrino is not converting into a muon, so this cannot be a charged current process. We don't observe the neutrino final state, but it is there, of course. And so this can only be understood in terms of a neutral current process. Okay, so it is a scattering of a muon neutrino with one of the quarks of the nuclei which are inside the bubble chamber. Okay, of the frame. So let me remind once more that in both cases, the characteristic signature of charged current interaction, so the presence of a muon in the final state, is not observed. And therefore, these kind of events could only be understood if the process were regulated by weak neutral current. And this was indeed the experimental proof, okay, of the existence of neutral currents, and this was published in this paper in September 1973. So observation of neutrino-like interactions without muon or electron in the Gargamel neutrino experiment. Okay, very extremely famous paper. Now, so this was the experimental proof of the existence of weak neutral currents, but it was, in a sense, an indirect proof. Okay. The direct proof is really observing the Z boson. Now, the search for the Z boson and the W boson as well, both predicted by the theory, okay, took place along the 70s and then the 60s, maybe, 70s more. And it was quite challenging, okay, because these are very heavy objects. Okay, the W's are 80 GeV, the Z is 91 GeV, so you need a high energy accelerator and also a smart experiment to be able to detect those. Okay, and the discovery of the Z and the W's occurred in 1983, so 10 years later, still at CERN, by two competing experiments: the UA1 experiment that you see here, and the UA2 experiment that you see there. Okay. The detectors were completely different. Okay, they adopted, let's say, complementary strategies for detecting these particles. They both observed the Z and the W's, but the spokesperson of the UA1 experiment, that was Carlo Rubbia, was, let's say, more motivated, probably. He had only a few events in hand, but this was sufficiently for him to announce the discovery. And so they were faster. Okay. So at the end, the UA1 officially got the discovery first, which was later confirmed by UA2, and Rubbia got the Nobel Prize for this. Okay. So how this experiment worked? Okay. So the intuition of Rubbia is that when you are colliding at high energy a proton with an antiproton, of course, at the elementary level, the collision is between a quark or a parton of the proton with an antiquark or an antiparton in the antiproton. Okay. So if, for instance, you allow for a collision between an up quark from the proton and an anti-down quark from the antiproton, okay, then you can form a W+, okay, which then eventually decays into electronic channel, for instance. Or if you allow for interaction between a d quark in the proton and the anti-up quark in the antiproton, again, you can produce a W-, which decays into, for instance, electronic channel. Okay. Or if you consider U bar or D bar interactions at the elementary level, then you can form a Z0, okay, which of course decays into electron positive, platinum minus, etc. Okay. So this was the idea. The idea was brilliant, but in order to be put into reality, this required a lot of effort, also from the technological point of view. The reason is that at that moment, in the early 80s at CERN, there was not a proton-antiproton accelerator or a proton-proton collider, but a proton-proton collider. This was the SPS, which is still active at CERN, the super proton synchrotron. Okay? Which is actually a fixed target. So we have a proton beam, and then there was fixed target experiment all around. So the idea of Rubbia was to transform this super proton synchrotron into a proton-antiproton collider. Okay. In such a way, you enhance the probability of a quark-antiquark collision in the center of mass. Okay, and so you enhance the probability to create and observe the W's and the Z. Is that clear? Now, Again, from the technological point of view, this was a challenge, a real challenge, because okay, let me ask you, how would you create a beam of protons? Try to think. What are protons? Hmm? Hydrogen nuclei. Indeed. So you start from a hydrogen gas, atomic hydrogen, una bombola di idrogeno, una bomboletta anche piccolina, ce ne basta pochissimo. So what you do, you open your hydrogen vessel, then you allow some atomic hydrogen to flow, then you strip the electron, so at the end you get only proton. The proton is charged, so you can apply an electric field, so it gets an accelerator, and then you can accelerate it at many steps. At the end, you can get whatever energy you want. Okay, so producing a proton beam is easy. Okay, you just need così le bombole in inglese. La bombola, a bottle of hydrogen. That's it. But how can you produce an anti-proton beam? That's a bit more complicated. We don't have anti-hydrogen in a bottle. You cannot find in the market. Any idea? So in order to have a beam of antiproton, we have to create, first of all, antiprotons. And then we have to focus them and to accelerate them. So there are many steps. So how can you create antiprotons? Antiprotons you can create in high energy proton nucleon collision. Suppose you have a high energy proton into a target, whatever nuclear target, whatever beryllium or whatever target you want. At the end, you have a lot of particles in the Fanor channel, okay? Pions, kaons, protons, antiprotons as well. Then you select your secondary antiprotons with the proper magnetic optics, so with magnets essentially. So you disentangle the antiproton thanks to their charge to mass ratio with respect to the other particles. You inject them into some linear accelerator, you start to accelerate and you have to accumulate. So we have to accelerate them and accumulate such to have enough density, okay, enough beam intensity. Otherwise, your experiment is not, you cannot perform, okay. Suppose now you have done all this, so you have created the antiproton, you have injected into an accelerator, you have also accelerated this. This is not the end of the story. There is another complication here. The complication is that whereas your initial proton beam is monochromatic because you tune your energy in your accelerator, so you get whatever 100 MeV proton, 100 GeV, whatever you want. But the antiproton come as a reaction product, so they can have any possible value of the energy of momentum. Okay, so you have to make them monochromatic, such that at the very end you can collide two monochromatic beams of protons and antiprotons, okay, with enough intensity. How to make this? This was another challenge. And this required this brilliant idea by Van der Meer, the guy here shaking hands with Rubbia. He had the idea of developing a new kind of cooler, where cooler means that something that allows your momentum spread of your antiproton to be squeezed, such that at the end you get a monochromatic beam. Okay, so the moment I have a large spread at the beginning, you have to find a way to squeeze this momentum distribution such that you get at the end a monochromatic beam. So the idea of this stochastic cooling is depicted here. Okay, so suppose there are antiprotons running in this storage ring. Okay, so they are stored, they are maybe already packed into bunches, but the momentum spread is very large. So there is essentially a pair of detectors in two different places around the orbits of the antiprotons. Okay, and these detectors stochastically pick up some of the antiproton in the beam. Okay, they read their momentum. They calculate the difference between the measured momentum and the nominal momentum you want to have, and so they send a signal, okay, to another detector, to a kicker, actually, to a magnet. Okay. So when the magnet receives the signal and that antiproton passes through, the magnet corrects the momentum, okay, to the proper value. And this is done stochastically after thousands and thousands of millions of, actually billions of orbits. Okay. So at the end of this process, you get a almost monochromatic beam of antiprotons. Once we have done this, so it is now sufficiently intense and monochromatic, you can finally inject into your collider and make collision with the proton beam from the other direction. Okay. So now back to the physics. We can think the colliding proton. Of course, van der Meer got the Nobel Prize together with Rutger for this idea. Okay. Without this idea, the experiment was not doable. Now, we can think the the colliding proton-antiproton as we know, bunches of partons, okay? And since the energy is very high, we can work in the collinear approximation as we studied already, so we can neglect all the transverse momenta of the colliding parton. So essentially, we consider we have a proton beam, an antiproton beam, which is just bunches of partons from one side and a parton from the other side, okay, which are colliding. Now, indeed, if you get a d bar collision, you provide a W minus, or a d bar you get a W plus, or if you have a u bar d bar, you can form a Z0. Now, what is the problem here? There is another complication, because in your machine, in your accelerator, you can decide, you can tune the energy of your beams. And so you can decide or tune the center of mass energy for the proton-antiproton collision, okay? But what we want here is not the center of mass energy of the proton-antiproton collision, but the center of mass energy of the quark-antiquark collision. And you can never measure the energy of the quark inside the proton, okay? So the idea is that in order to create a W here, the center of mass energy of this quark-antiquark collision must be at least 80 GeV, the mass of the W. Similarly, if you want to create a Z0, the quark-antiquark center of mass energy collision energy must be 91 GeV, okay, to create the Z. But you cannot decide the energy of the quarks. You can decide the energy of the proton or your beams, okay? So what we know now from the structure of the proton that we studied a couple of weeks ago, we know that quarks inside the proton share part of its momentum. And this fraction of the momentum carried by the quark is given by the X-Bjorken variable, if you remember. So the higher the energy of the two beams, the higher the probability that you get a quark and antiquark colliding with the proper center of mass energy. So at least 80 GeV if you want to form a W, or at least 91 GeV if you want to form a Z. Is that clear? You can fix only the beam energy, and so the center of mass energy proton antiproton. But in order to have a sufficient probability to have the proper center of mass energy at the quark level, you have to increase as much as possible your beam energy. Okay. Now, the beam energy that they used was initially 540 GeV. Okay, the center of mass energy. Okay, which is clearly much higher than 80 or 91. Okay. So they had 270 GeV per beam. And at this energy, one can estimate that the average value of the X-Bjorken is 0.15. Okay, so essentially, at this energy, which is not extremely too high, in average, quarks carry 15% of the proton momentum. Okay, and since this is a quite large value of X-Bjorken, we are in the valence quark region. We are dominated by the valence quark. Okay, if you remember, valence quark corresponds to high X, and C quarks and gluons to low X. Okay, this we studied recently. So essentially, at the center of mass energy of the superproton synchrotron, the collision is mainly between valence quarks. So a d valence quark from the proton with the u bar valence quark from the antiproton. Okay. Now, clearly, the probability to form a W or a Z increases with the increasing beam energy. Okay, so they started with 540 GeV, but it was not sufficient. So at the end, they managed to even increase the beam energy, center of mass energy, up to 630. Okay, such to enhance the probability of the quark-quark interaction, the proper energy. These are very rare events. Okay, so the cross-section for the formation of a W or of a Z in a proton-antiproton collision is very small, in particular 530 picobars for the W and an order of magnitude less for the Z, so only 35 picobars for the Z. Okay, and this has to be compared with the total proton-antiproton cross-section, which is a 50 millibar. Okay, so it is essentially 8 or 9 order of magnitude smaller than the total proton-antiproton cross-section, collision cross-section. Okay. So in other words, these people had to look for extremely rare events over a huge background. Okay, another challenge. And so the only way to find out these very rare events in a huge background was to, of course, look for the most clean event topology as possible. Okay. So suppose you create a W. Okay, and then the W decays into quark-antiquark. Quark-antiquark hadronize, and so at the end you get two jets. Is this a good channel to look at? No, it is not. Why? Because the remnant of the proton and the remnant of the antiproton, so the other quarks, okay, which are smashed in the collision, they also hadronize. So at the end you have several or even many hadron jets. And so it is hard to identify which one is the one coming from the decay of the W, which one is just background. Okay, so hadronic channels are not the best choice. Okay, you will be killed by the background. The better choice was to look at semi-leptonic decays. Okay, so where now the W or the Z decay into leptons. The W can be into a charged lepton and its neutrino, and the Z into a lepton antilepton. Okay, Electropolitan or plus minus. And one has to look in particular to events where these two leptons share a very large transverse momentum. Okay, so the two protons are colliding in the collinear direction. Okay, along the Z. Okay, if you have a very large transverse momentum carried by only leptons. Okay, and when the sum of these transverse momentum essentially equals the mass of the W or the Z, then you are done. This is most likely a good event. Okay. And this is the technique that they use indeed. Okay, so you see here, for instance, for the Z, this is the energy release in the calorimeter. Okay, we have two sharp peaks at something like 40 and 50 GeV. Okay, so in the transverse plane. And so when you sum the energy of these two electrons, then you end up indeed with the energy of the Z. Okay, so this was indeed one clear evidence for the formation of Z in this event. For the W, it's more complicated because you create in the decay an electron and a neutrino. The electron you can detect, you can observe the energy released in the calorimeter. The neutrino you cannot, of course. But if you know, if you measure precisely the momentum of the electron, and you know precisely the center of mass energy, and so you can represent precisely the kinematic of your event, you can deduce the momentum of the neutrino, so the missing momentum, just by difference. The total minus what you detect. What is missing is the fractional momentum carried by the neutrino. Okay, and this is indeed what they did. So at the end, the two experiments found so were able to reconstruct the invariant mass in the final state in this way, and they found these values for the mass of the Z and the W. So these are the two experiments. Okay, E1 and E2. At the time, with a rather large uncertainty, of course, they only observed a handful of events. 5, 6 events, and they claim the discovery. These are now today's values, okay, which are of course consistent with those already measured by Rubia and friends, but with much larger precision, of course. Okay. So how do we get all this precision in the mass of the Z and the W? Okay, we had to wait for a next generation of accelerators. Okay. So the super proton-antiproton synchrotron made the discovery. Okay, they had enough central mass energy to make the discovery. Now we want to study carefully and characterize this object. So you need a different machine. More specifically, you need a high-energy electron-positron collider. Why electron-positron? Because essentially, in the initial channel, you just have leptons. So pure QAD. And this you can calculate perturbatively, precisely. You don't have any QCD background. So what you need is a high energy because you want to produce a lot of W and Z, but also clean processes. So this was the idea to construct the LEP collider, the plus-minus collider at CERN, which operated from 1989 up to 2000, so up to 20 years ago, essentially. And it was indeed the highest energy Electropolitan collider ever built, still, okay? Now, the circular accelerator was located in a 27-kilometer circumference, 100-meter underground, in a tunnel, and it is exactly the same tunnel that today hosts the Large Hadron Collider, okay? So the Large Hadron Collider used the same tunnel, okay? And of course, substitute completely the LEP in the early 2000s. Electron and positron were circulating in opposite direction and collided at 4 different interaction points in correspondence to 4 different experiments: Aleph, Delphi, L3, and Opal. And you see here a sketch of the 3 detectors. These were all typical collider detectors with this vessel shape, like onion-shaped detector with different layers of different detectors. And they were indeed all essentially general purpose detectors. They were not specialized for a single thing, but they could essentially detect anything and study anything. But of course, the main scope was to characterize the properties of the Ws and the Z, plus many other things. So in the first era of LEP, so from 1989 to 1995, LEP operated a center of mass energy close to the mass of the Z. Because you want to create Z, okay? In this case, the full center of mass energy of electron positron can be used to the creation of the Z. You don't have quarks, you don't have to share this with the X-Jochen, you just have 2 electrons, okay? So if you tune your energy to the mass of the Z, you're done. Of course, modulo the small cross-section. And so in this way, they were able to accumulate something like 17 million of Z events, to be compared with the 5-6 event measured by Rubbia. And so, of course, this allowed to measure the properties precisely. Then in the second era of LEP, so from 1996 up to 2000, the energy of the machine was increased, okay, such to reach essentially twice the mass of the W. So such that we can create a W plus W minus in plus minus collision, annihilation, okay? So the energy was increased up to 209 GeV, and they were able to accumulate 30,000 events for W plus W minus production. So let's consider, first of all, the Z, okay? Let me now concentrate on the characterization and measurement of the properties of the Z boson. So at LEP, the mass and the width, the decay width of the Z boson was determined from the center of mass energy dependence of the cross-section, the annihilation cross-section, okay? So you are annihilating electron positron by using 2 colliding beams. You create with certain probability the Z, and then you observe the decay channel of the Z. So fermion and anti-fermion in general. And at center of mass energy close to the mass of the Z, as we know, the cross-section is described by Bragg-Wigner. So we are essentially producing a Z resonance, okay? So you see here the Bragg-Wigner function that we already discussed, but let me give you some more details in the blackboard. So we have cross-section for electron, plus minus into fermion in general, so the function of the energy and the momentum. And that's why now the full special video for 5. Then we have the debris wavelength squared. Then we have the angular momentum multiplicity, so it's 2J plus 1, and then we have 2 the spin of the electron plus 1 times twice the spin of the positron plus 1. And then we have the Bragg-Wigner dependence, so it's E plus minus, if you like. And we have the final state, fermion 4, and then we have the ER squared plus down the 12 over 4. So what we have here, the debris wavelength of of our projectiles, the angular momentum multiplicity that you have to take into account first. And then we have here the partial decay width of the Z, which is here in between the resonance, into Electropolitan or into any final state fermionic term. Okay? Then this is the center of mass energy, this is the energy of the resonance, at the center of the resonance, and then this is the total decay width of the Z. Okay? So this is the very linear formula for inelastic process that we studied already in a different scenario. So let me write down this. So the W wavelength by 2 pi is just the reduced W wavelength, that is h bar divided by mu to p. Now, in a symmetric collider, it is square root of s divided by 2. This is for a symmetric collider, as it was the case of the length. Okay, so the electron plasma beam had exactly the same energy. And so, in natural units, this is just 12. Now, let's compute this term here. So we know that the spin of the electron is equal to the spin of the positron, is just 1 alpha. And we also know that the spin of the Z, the angular momentum of the Z must be 1, because the Z, as we studied, but as you know already, it is a vector boson. Okay? So the spin must be 1. So when we put all these together, our 2jz plus 1 divided by 2, st plus 1, 2, st plus 1, becomes 2, so 2 times 1 plus 1, 2 plus 1 half plus 1, 2 plus 2 times 1 half plus 1. And so this is just 3. Okay, so now we can substitute here. Let me just remember this. So this is a 2 divided by 2 of S. So we have to take this squared. This is 4 pi. Then we have the square of this, so this is 4 divided by S. Then we have 3/4. And then we have the radical part. Now, here we can write square the pi divided by S. And now we can substitute here. The energy is just square root of S, and the energy of the resonance is just the mass of the Z boson. Okay. So I will do this way. So when we get now at the resonance, so when the square root of S for S is equal to n squared Z, then this guy becomes 12 pi divided by S, so by n Z squared. And then we have gamma A plus minus gamma fermion fermion. This guy cancels here, okay, because of the resonance, these two are exactly the same. This disappears, and then we have just this total width. So up to now, this is the general formula. Then we calculate it exactly on the top of the resonance. Okay, so from the center of mass energy equals the mass of the Z. And so this is what we get. Okay. Okay. So the cross-section peaks sharply at when the center of mass energy corresponds to the mass of the Z, okay, and in that limit, it gets this value here, the one that we derived. So this is the cross-section at the maximum, on the top of our resonance. Now, this is not the end of the story, because in order to correctly reproduce the Z resonance, and so to correctly extract from it the mass of the Z and the width of the Z, you have to at least consider a few higher order 3D diagrams, which are reported here. So you have to take into consideration the fact that your incoming electron or your incoming positron can radiate a Bremsstrahlung photon, okay, which is a pure QED process, so it is a real photon. Because when this happens, and this can happen, of course, then clearly the center of mass energy at the vertex will be different, because part of the momentum is taken by the real photon, is taken away. So one has to correct your Breit-Wigner, in a sense, in order to take into account for this higher order initial state effect. And the effect is actually to distort the shape of the Z resonance. Okay, that's why you want to correct for this. The good news is that it is a pure QED process, so it can be easily calculated in perturbative theory. And so this is now the result, okay? So the points are experimental data. The full curve is the Z resonance before correcting for the initial state effect. And then the dotted one is the real one after unfolding for these initial state QED radiations. Okay. So once you unfold now your results, you get to the proper resonance shape, then you can use this to derive the mass of the Z and also the decay width of the Z as the full width of maximum. So in particular, from these measurements, they obtain the mass of the Z, 91.1875, whatever, with a huge precision. So look where the uncertainty is, okay? So the precision is indeed at the level of 0.002%. Okay, and it was possible because they were allowed to accumulate a lot of statistics. Okay, because the machine was tuned indeed for the creation of Z. So how can people reach such a level of precision? Okay, so a level of 0.002%. Well, they had to take into account any possible systematic effect, including the gravitational pull from the moon, le maree. Le maree, sapete, agiscono sul mare ma anche sulla roccia, con un effetto molto più piccolo. But the gravitational pull of the moon was enough to distort the rocks surrounding the lect by something like 0.15 millimeters, okay, over 4.3 kilometers, and this was enough to generate a shift in energy by plus or minus 10 megaelectron. So they had to take into account this. And then there was another nasty effect that was very hard to understand at the end. Like every day at a certain time, there was a shift in the energy in the machine. And it took a lot of time to understand that this was the leakage curve from the railway. There was a high-speed train passing through Geneva that was dispersing energy into the ground. And this was at the end affecting the dynamics of the machine, and so the energy will be fantastic. Quando arrivo a questo punto del corso mi viene la pelle d'oca. Okay, so they were really clever. They made it, okay? Now, not only they derive precisely the mass of the Z, but also the decay width, okay, the total width, which is of the order of 2.5 GeV, okay, so it's very, very large. And a very, very large decay width corresponds to a very, very tight decay time. Okay, so the decay time corresponding is of only 2.6 10 to the minus 25 seconds. So in other words, as soon as you create a Z boson, this immediately decays, okay? Why it's so short, or why is the decay width so large? Because the mass of the Z is so large that the phase space available in the decay, so the energy available in the final state, is so huge that it immediately can decay in any possible channel. In particular, the Z can decay in any pairs of fermions, so fermion antifermion, allowed by energy conservation, so such that the mass must be, of course, smaller than half the mass of the Z. Okay, the Z cannot decay into top anti-top because the top quark is heavier than the Z. This will not be allowed. Okay, but otherwise can decay in any fermion antifermion pair if the mass of the fermion is smaller than half the mass of the Z. And so you see here the full collection of possible decay modes of the Z. Okay, it can decay into electron positron, U plus mu minus, tau plus tau minus, UU bar, DD bar, SS bar, CC bar, BB bar, not TT bar because it is too heavy. Okay, and also into neutrinos. Okay. So we can now collect all these terms into three main contributions. Okay, so the three leptonic contribution, okay, which are assumed to be the same based on the lepton universality that we studied yesterday. So this can be just a generic charged lepton. L can be electron, can be muon, can be tau lepton. The hadronic, which is the sum of all the decay into quarks, antiquarks, and then the neutrino sector. Now, the fantastic thing was that the precision reached at LEP on the decay width, on the measurement of decay width of the Z, was high enough to allow for a possible check for a fourth family of leptons. What is the idea behind this? Suppose that in addition to electron, muon, and tau, there is another family of electrons, okay, Pippo, which is extremely heavy, okay? So is heavier than half the mass of the Z, so the Z can never decay into Pippo anti-Pippo. But if it is an electron family, it comes with a neutrino, and neutrinos usually are light, okay? So possibly, if this fourth family of electrons would exist, then the Z could, in principle, decay into these neutrino types, okay, the fourth family. And the precision of LEP was enough to test this, okay? And so indeed, they did this test, okay? So the total width of the Z is indeed the sum of 3 times that of the charged leptons, okay, based on the lepton universality, the total width of the quark decays, and then we have the neutrino sector. So instead of putting 3 here, let's put a free parameter, and so a free number for the number of families of neutrino families, okay? So you can now invert this formula, and you get that the number of neutrino families, and so the number of lepton families in general, is given by this ratio here. Where now in the denominator, you see, they put a very precise standard model prediction for the decay of the Z into electron-neutrino, electron-neutrino. Okay, so the numerator you can measure precisely at LEP. The denominator is a precise prediction from standard model, so you can infer the number of lepton families this way. So indeed, all these partial decay widths can be measured at LEP by knowing the cross-section of the top of the resonance, okay? So by measuring these, you can, and knowing the total width, the mass, etc., you can measure all these contributions in the numerator. The denominator was known from standard model, and now when you take the ratio, you get exactly 3 within the experimental set. Okay? So this was a strong, very strong experimental proof that indeed there exist only 3 families of leptons. If there were a 4th family of leptons, then the resonance of the Z would be different, would be higher, and even a little wider also. Okay, so this would be inconsistent with the experimental data. There would be 166 MeV larger than observed. Okay, final words about the Z. Yes. So let's now look at the Z resonance in the full shape. So here we have the electron positron into quark antiquark cross-section. Okay. The dotted line is the QAD contribution, and the full line is the QAD plus neutral current contribution. Okay. So what we see here is that at low energy, so here we have the energy in the central mass. At low energy, essentially below 40 or something GeV, essentially the total cross-section corresponds to the electromagnetic process. Okay, the energy is too small to allow for the Z process to be important. By increasing energy, so in the region between 50 and 80, something like that here, right here, then the contribution from the Z, so from the weak neutral current, becomes sizable. Okay, Then at the resonance, it becomes totally dominant, of course. Okay, so the electromagnetic is killed by 4 order of magnitudes here, essentially. So it is now purely weak. And then when you go at even higher energy, or very, very high energy, the total is essentially twice the electromagnetic. This means that the two asymptotically becomes, the two contribution becomes equal, asymptotically. And indeed, this is the region of the electroweak unification, okay? Where you only have essentially a unified coupling. Ok, let's make a break. Ripartiamo alle 12:15, va bene? Ok, Marianna, vedi la slide?
Sì, sì.
Okay, so we spent the first part of the lesson describing the neutral currents, and then we discovered the W and the Z and the properties of the Z boson, so resonance, etc. So we study next week how the coupling of the Z to the other standard model particle is provided in the electroweak framework of the standard model. And let's now focus on the Ws, okay, the properties of the Ws. The Ws were discovered by Rubio together with the Z, okay, at CERN in 1983, but then they were also characterized and studied in precision at lab. So the double boson can also be produced in E plus imagine annihilation, but only in pairs, okay, because you have to allow for electric charge conservation. Okay, the Z you create is electron positive and a neutral, but in order to create a W plus, you need to create in pair with a W minus. And so, in order to create a W plus W minus pair, you need a much higher energy than the one needed to create a Z. And so, the center mass energy should be at least twice the mass of the W. And this was reached at lab in the second part of the experiment, with energy as high as 209 G. Now, suppose now you create your Ws, okay, and the process is depicted here. So you're annihilating electron positron into a Z, and then the Z decays into W plus W minus, which further decay into their state decay. And indeed, the W can decay either leptonically or hadronically, so either into lepton and neutrino or into quark and quark. And so, since we have two of them, okay, we have essentially three different event topologies. Fully leptonic, where both the Ws decay electronically, semi-leptonic, where one decays electronically and one into Q bar, and fully hadronic, where they both decay into quarks. As you see here, example of these three types of events measured at lab. So the first one is a pure leptonic decay. So both Ws decay into a charged lepton and a neutrino. The neutrino, of course, are undetected, but you see here the release of some energy in the calorimeter by the electron and also by the moon, which is escaping here. Okay, the moon is much more penetrating, so it can reach the outermost layer of the detector. Now, the second example is a semi-leptonic decay. So one W goes into the lepton and neutrino and the other into quark. So you observe still your electron here, a missing neutrino somewhere, and then two jets of hadron, because the quark antiquark hadronize into jets, as we know. And then the last category is when both Ws decay into quarks, and so we observe four hadron jets. Now, differently from the Z, the production of the W at lab is not a resonant process, okay, because you have to produce two of them with opposite charge. And so the mass and the width of the W, so essentially the main properties of the W, were determined through the direct reconstruction of the invariant mass in the final state, so of the decay products. A precise determination of the W mass and width can be obtained by reconstructing the four momenta in order to construct your invariant mass, okay, in both cases. So either you have a hadronic decay or semi-leptonic decay. And so you see here an example. So let's consider, first of all, both Ws decay into quarks. So we observe four hadron jets in the detector. Then we reconstruct the mass of the first W as the invariant mass, okay, as the two of these hadron jets, okay, so by reconstructing their four momenta, and the same for the second one, okay. What about a semi-leptonic decay? In this case, one of the W decays into quark antiquark, so you get two hadron pairs, and the other into lepton neutrino. Okay, so what you observe is two jets, one lepton, and nothing else, because the neutrino isn't detected. Also, in this case, you can reconstruct the final state invariant mass. For the quark, it's just the same, okay, by reconstructing the four momentum of the quarks. For the lepton case, it's a bit more complicated because you don't observe the four momentum of the neutrino, but you can reconstruct it as a missing four momentum. So you know the total for momentum of the reaction, you subtract all those that you measure, what is missing is the one of the neutrino that escapes. And so you can take the average of the invariant mass of the two W's in the decay, okay? And then you can now report these into graph, so as a function of energy, and you find that the invariant mass peaks around the mass of the W, which is 80 GeV, 80.4 GeV. And so by precise measurement of this type, people at lab was able to obtain this precise measurement of the mass and of the decay width. The decay width is still very large, okay, 2 GeV. It's not as large as the Z, which is 2.5, but still very large. And this means that indeed the decay time of the W is extremely short for the same reason. Now let's characterize now even more the decay modes of the W into all possible time states. So the W's, first of all, are bosons, okay, with spin 1, so vector bosons, and they come with 3 orthogonal polarization states. 2 are transverse polarization modes, okay, corresponding to circularly polarized states in one direction and in the opposite, and the other is a longitudinal polarization state. Let me remind you that real photons have only 2 polarization states, the 2 circularly polarized states, if you remember. Okay. In this case, we have 1 additional polarization state, the longitudinal, and the reason for that will be clear next week. And we will understand that this somehow is obtained through the Higgs mechanism and is related to the fact that the W is a massive boson, whereas the photon is not. Okay, so the mass of the W requires this additional polarization state. Now, similar to the photon, we can write down the wave function of the W as a plane wave times this polarization vector. Okay, where the index lambda takes into account the 3 possible polarization states, minus, plus, and longitudinal. Okay, so let's calculate now the partial width of the W into electron neutrino decay. So suppose we have a real W, in this case into electron and an electron antineutrino. So we have one vertex. No. We have the 4 momenta, P1, P3, and P4. Okay. Now, the wave function of the W, as we saw before, is the polarization vector, where lambda identify the 3 polarization states, times a plane wave, P minus I to X. Or this Q that we call T1, the momentum of the W. So this we can also write as epsilon mod lambda e to the minus I P3 plus P4 X. The reason for that is that it is an S channel, okay? And so the momentum, the incoming momentum must be the sum of the two in the final state, okay? Now, what about now the wave function of the electron and the neutrino? This we can write in terms of the spinor, or the direct spinor. So for the electron, we have UP3, and then we have the plane wave on the top, I P3X. And for the antineutrino, we have U P4, and now we have the complex conjugate, so plus I P4. Because it is an antiparticle. Okay, now we have all the ingredients. Let's calculate the matrix element. So we have, first of all, the W. And we have the current here. So we have U bar P3, and then the complex conjugate of this guy here. So this comes with a plus sign. E I P3 X. x. Then we have the vertex factor minus pi g 2 square root of 2 gamma mu 1 minus gamma 5. The one that we derived in the V minus I theory, okay, which works for charged currents. And then we have the antineutron, which is now, sorry, the D. It's not the P, it's an antiparticle spin. There is a D before, and then E2I before X. Now, all these exponentials go away. And so we have minus I d divided by square root of 2 epsilon mu lambda. And then we have the current mu bar 3 mu 1/2 1 minus 5 d equal. Let's divide this in an equivalent way as minus I d square root of 2 epsilon mu lambda mu bar 3 1/2, and then we put here gamma mu 1 minus gamma 5, and then we have the antineutron. You remember from the last week that we can write down this piece here in a proper way in terms of the gamma mu and gamma 5 method. This we show to demonstrate last time, so let's now just use this result. So this is minus I d over square root 2 epsilon lambda mu. Then we have the u bar 3. Then we have 1/2. And now this block here becomes 1 plus gamma 5 gamma mu. Gamma mu 1 minus gamma 5. And then we have d before. Let me continue here. So this we can write as minus I g 2 epsilon. And now we have the u bar 3 1/2 1 plus gamma 5 the gamma mu, and 1/2 1 minus gamma 5 b before. Now, this is the left-handed projector operator. The right-handed, sorry. This is the left-handed. So now we have the right-handed projector acting on an adjoint spinor and for a particle, and the left-handed operator acting on an antiparticle spinor. Okay. So the result of this is minus pi g square root 2 epsilon mu lambda. So PR of the joint spinor gives us UL, U bar left, P3. Then we have gamma mu, and P left on an antiparticle spinor gives us U bar. So LPR. So we have some quantum here. 2, then we have the correlation factor. And this is just our current, so we can call limbo left, right, where left is the lepton and right is the anti-lepton of is the only way they can couple with the charge current. Okay. No, ma non ho condiviso. Marianna, mi sa che tu non hai visto niente alla lavagna. Non
io ho visto, però ho dovuto switchare insomma, i riquadri di visualizzazione. Non so se nella registrazione poi però si vede la lavagna.
Che si vede lo stesso piccolino, comunque poi vi do le scansioni, quindi lo trovate poi nel PDF.
Mi sono dimenticata di ricordarglielo. Comunque io l'ho vista.
Va bene, comunque poi nelle scansioni avete poi tutto passato. Allora torniamo sulla slide. So this was our result, okay? So this is a matrix element for the decay of a real W into electron antineutrino, okay? In terms of the left-handed and right-handed chiral spinors for particle and for fermion and antifermion. Now, the mass of the W is huge, is 80 GeV, okay? So when it decays into electron and neutrino, both electron and neutrino are ultra-relativistic, of course, okay? There is a lot of energy available in the decay. And so, since they are ultra-relativistic, essentially chirality coincides with helicity, okay? And so we can safely replace, in this regime, the left-handed spinor with a negative helicity adjoint spinor, and the right-handed antiparticle spinor with a positive helicity antiparticle spinor, okay? So we are interchanging the chiral eigenstate with the helicity eigenstate, and this we can do because we are ultra-relativistic. So we can neglect the masses. Now, this is the way to calculate this current, and so the matrix element. Now we want to calculate the decay rate for this specific decay here, okay? So what we have to do, we have to calculate, now we have to average the matrix element over the three possible polarization states, okay? So this is just 1/3 and the sum of the 3 squared. And this can be shown, we will not derive this, but this is just given by this quantity here. So it's proportional to the square mass of the W. Then what you do, you take this spin average squared matrix element, you put into the general expression of the decay rate, okay? You calculate the integral over the phase space, or the solid angle, and at the end, the result is this guy here. So, where P star that you see here is the momentum of the electron or the antineutrino in the center of mass frame, okay? As we derived in the very beginning. Now, since we can neglect the mass of the electron and of the neutrino, of course, given the large energy in the process, in the decay process, then the momentum of either the electron or the neutrino in the center of mass is equal to the energy, which is just equal to mass, to half the mass of the W. Okay, this is all we have in as energy in the center of mass. Okay, so we can just substitute here instead of P star the mass, half of the mass of the W. Okay, and so what we obtain at the end of this story is the partial wave for the decay of the W into electron neutrino. Okay, in terms of quantities that we can calculate or measure. Okay, we have the coupling, the mass of the W, and some constant. Last time we also derived the connection between G squared and the Fermi constant, if you remember. So you can also write this in a totally equivalent way in this way. And when you calculate, you just put numbers, okay? So the value of the Fermi constant is 1.1666 10 to minus 5. The mass of the W, 8 GeV, and then you convert the result in MeV, you obtain 225 MeV. Okay, so what we got here is that the partial width for the specific decay mode, the W into electron antineutrino, is 225 MeV. Now we want to calculate the total decay width, okay, and compare with experimental results. So in order to calculate the total, you have to take into account all possible decay modes, okay? But the good news is that we don't need to repeat this calculation every time for each decay mode. We can just use a simple trick, as I will show in a moment. Okay. So first of all, things becomes easy because we can assume electron universality. Okay. So the decay width of the into electron neutrino or muon antimuon neutrino or tau antimuon neutrino is essentially the same. Okay, once you correct for the small mass differences. And so we can assume for all of them that the partial width is 225 MeV. Now we have to take into account the hadronic decay mode, so the decay of the W into quark-quantic quarks. Okay. Of course, the W can decay in everything except the top quark because it's too heavy. Okay, so it can decay in the 3 lepton families and also all possible quark-antiquark combination, excluding the top quark. And in calculating now the decay width into quark-antiquark, we have also to consider the proper matrix element of the Cabibbo-Kobayashi-Mascaro matrix that we discussed yesterday. Okay, because the coupling is yes universal, but you have to take into account the mixing of quarks. So, for instance, the decay of the W into a du bar is 3 comes from the 3 possible colorless states of the final state quarks. Okay, we have 0 color in the initial state. We have to have 0 color in the final state. So we have 3 possibilities: red, anti-red, green, anti-green, blue, anti-blue. This is the factor of 3. Then we have the proper element of the CKM matrix squared. Okay, the UD in this case, and this just we have just to multiply this by the width calculated before. So the decay width of the rectum, which is 225 MeV. So for instance, let me just take some example. The lambda CS, so the decay of the W into a strange anti-charming quark, this is 3 times the square of this CKM matrix element and then the width of the electron. So it is 3 times 0.99, which is this matrix element, and then the width of the electron, 225. And you get whatever, 660 MeV. Then, for instance, let's take the last one, UB. So this guy here, UB is a transition between the first family and a third family. So it is highly suppressed, as we said yesterday, due to the quark mixing. So we still have the factor of 3, but now the matrix element is very, very small, and square is even smaller. And then still we have 225. So at the end, it is just 0.006, and so on. So you can calculate all of them. And so let's do this in the exercise. Okay, so the electronic modes start with the W plus, so it is E plus neutrino, mu plus neutrino, tau plus neutrino tau. Okay, these are the 3 possible electronic modes for the W plus. And for the quark modes, we have all the possible combinations. So U bar, or C bar, or U S bar, or C S bar, or U B bar, or C B bar. So this is up, on, sharp branch. So we are considering all the combinations that exchange 1 unit in electron charge, okay, without considering the top quark. So we have this one here, 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 and then what do you see? Okay, that's it. So these are all the possible decay modes of the W. Okay. So the W plus into positron electron neutrino. Let's take this as our reference. So this we take the value 1. Now, for the electron universality, it must be the same also for the other 2 electron channels. Okay, 1 plus neutrino mode 1, and tau plus neutrino tau is also. Stesso problema di prima.
Sì, esatto.
Devi dirmelo, io lo so. Okay. And this is also 1. Okay. So the electron part is trivial. Let's now go to the quark part. So the W plus into U B bar. Okay. So now we have 3 because it's the number of colorless combinations. red and green point of view. Then we have the squared UV CKM matrix element. And so we have 3 times 0.974 u squared, this is 2.844. Now let me go quickly to all the others. The second is C D bar, which is 3 times DCD squared, which is 3. Now we have to pick up each time the proper element of the CKM matrix. Okay, so this is 0.225 squared, so this is 0.152. Then we have the W into US bar. So we have 3 VUS squared, which is 3 times is the same, 0.25 squared, it is just the same. Then we have the W into CS bar, so this is 3 times VCS squared, it is 3 times 0.973 squared, it is 2.840. And the plus now in the UV bar, so it is 3 times VUV squared, it is 3 times, it is a very small contribution, of course, 0.0035 squared, that gives us 3.6 10 to the minus 5. And the last one is the W plus into CD bar. So this is CD squared, that is 3 times 6.041 squared. This is 0.048. Okay. So clearly the largest are those that correspond to transition within the same port family. Okay. Then transition from the second to the third are suppressed, and the third are doubly suppressed, as we said yet. Okay. Now we can take the sum of these. Okay, so 1 plus 1 plus 1 plus blah blah blah, and we obtain 9.038. Posso cancellare? Allora, voi avete questi numeri, ce l'avete nel foglio, quindi avete un po' di spazio. Allora, now the partial width. So the lambda, gamma, electron, neutrino. For the electron universally is the same as the one in the moon for neutrino, and for the tau neutrino, tau. Okay, so it is 1 divided by the total. 1 divided by 9.038. Okay. This is 0.1106, so it is approximately 11.1%. Okay, so this is the branching ratio of the W into either of the 3 possible electronic channels, 11%. Now, for the UV, this is 2.846 divided by 9.438. And so this is 0.3149, so essentially order of 31.5%. C bar is 0.152 divided by 9.038, which is 0.0176. So this is called 1.7%. US bar the same. Then we have the CS bar. Like all of these, this is divided by the total. is the ratio. So this is 2.840 divided by 9.038, and it is again 31.4%. Lambda u v bar divided by total gamma is 3.6 10 to the minus 5 divided by 9.038, and this is 4 10 to the minus 6. And finally, lambda c bar divided by gamma is 0.048 divided by 9.038, which is 5.3 10 to the minus 3. The sum is, of course, 100%, because we are considering all the possible decay modes. Okay, so the three electronic decay modes are about 11%. Then we have particle code, they vary a lot depending on the CDM map. So depending on which kind of transition we have between the four families. Okay, you can have sizable contributions like this one, and you can also have very small contributions from ones. Okay, so if you sum up all these quark contributions here, okay, then it turns out that overall they are 6 times that of each lepton decay width. Okay, let's put it here. So the sum of all these right here is 6 times each of these, or the electron, or the moon, or the tau decay. Now, to make things more precise, you have to consider also in this case radiative effects. In particular, you have to account at least for a gluon radiation by one of your quarks. Okay, so in principle, you have to correct by this, and the correction is given here is alpha strong, calculated at the mass of the W. Let me remind you that alpha strong is a running constant, so its value depends on the energy scale. So alpha strong at the value of the W mass divided by pi. And so at the end you get a factor which is not 1, but is 1.0 something. Okay. So once you take this QCD correction into account, the branching ratio of the W into quark pairs, quark anti-quark, is not just 6 divided by 3 plus 6, but it is 6 times KQCD divided by 3 plus 6 times KQCD, because we are taking into account this gluon radiation. Okay. And once you do so, you just calculate this, you obtain 76.5%. Okay. So essentially, all these guys here account for 76 or whatever it is, 12.5%. Okay. All the hadronic decays. And this is in perfect agreement with the experimental value. The experimental value is written here is 76.41 plus or minus 0.27. And now, also considering this QCD correction, we can compute the total width of the W. Okay. Still, by using the first that we calculated before, so the one of the electron, and just by multiplying these by the proper factor, which is 3 for the 3 lepton families plus 6 for the quark families, corrected by the QCD radiation. So overall, this number is 9.2028 times the decay width of the electron into electron that we calculated before, which is 225, and so overall we get 2 point something GeV, which is again in excellent agreement with the experimental value, the one obtained at lab. Okay, and which, as I was mentioning before, corresponds to an extremely short decay time, 10 to the minus 25, because the mass is so high that the phase space is so favorable that as soon as you create a W, this immediately decays. Okay? Va bene, basta per oggi. Tutto chiaro? Allora, oggi abbiamo caratterizzato i bosoni vettori dell'interazione debole, il W e lo Z. Settimana prossima continueremo ancora sulle interazioni deboli, studieremo il sistema quantistico dei kaoni neutri, con sistema oscillante, e da lì introdurremo la violazione di CP nelle interazioni deboli. Questo è l'ultimo argomento prima di passare al modello standard vero e proprio, cioè all'unificazione eletrodebole, il modello di Salam, che cominceremo la settimana prossima e completeremo più avanti col meccanismo di Willis. Okay? Le lezioni, se seguiamo questo ritmo, dovrebbero finire il 3 giugno, cioè l'ultimo è il 3 giugno. Okay? Allora, interrompiamo la registrazione.